These are the notes on the half-life. As a quick recap, we've already talked about how nuclear changes are different from physical and chemical changes because you are actually changing which element you have. Remember, the only time that an element will change from one element to a different element, or even from one isotope to a different isotope, even if it's the same element, that's always a nuclear change. Okay, so now we've got a third kind of change to consider. We talked about the big two, the F words in nuclear chemistry, okay, that you can say in polite company. Okay, and to avoid confusion, just remember, fusion is found in the sun. That is the one where you're building up elements, making them bigger, making the nucleus, let's say, larger. Fission, on the other hand, is division. That is the one where you split the nucleus down or break it roughly in half. And we're going to see that there's actually other nuclear processes as well that can sort of break down a nucleus, but they are noticeably different from fission, which is like a big split in a nucleus. So remember, these are the two big ones, and you have to remember the difference. You have to be able to distinguish between nuclear fusion, which is forming larger nuclei by combining the smaller ones, and nuclear fission, which is splitting a large unstable nucleus into smaller nuclei. Okay, so it's forming smaller ones by splitting a large nucleus. Now, nuclear fission will not occur with every single nucleus. It takes a particularly unstable nucleus to allow nuclear fission to occur. We'll get into that more later on. Okay, but again, fission is division. That's the easy way to remember which one is which. Now we are going to be getting into other kinds of nuclear processes. Okay, we could call them all nuclear reactions, but some of them are kind of much smaller, so the word process is often used. Okay, many of these are going on all the time, all around us, sometimes even in our very own bodies. Okay, and these do not require special circumstances to occur. So for these natural processes that you don't need crazy conditions like inside of a star, or you don't need to trigger it artificially like in a nuclear power plant or a nuclear bomb, okay? These we measure using a half-life. So a half-life is an interesting concept, and we're going to do an activity that'll help you understand the way it works. It's a little bit, we would say, counterintuitive. It's not what you would guess. It's not what you would guess would happen. Okay, so half-lives measure what we call radioactive decay. It's called radioactive because it's throwing out radiation of some kind. Particle or electromagnetic radiation is thrown out. So what is a half-life? A half-life is the amount of time necessary for one half of the nuclei in a sample to decay to a stable isotope, or at least a more stable isotope. So that's an interesting definition. And at first glance, it might seem strange that they have chosen this, but it's what we call a statistical rate. It's a way of measuring something based on its probability, okay? And that's why it becomes counterintuitive. But just remember, a half-life is an amount of time. So here's my own little placard for half-life. The half-life is the amount of time it takes for half of a radioactive sample to decay to a stable isotope. So you may have noticed whenever I make one of these placards, it's going to be an important concept. This is one that you really need to grapple with and understand to understand radioactive decay and to understand nuclear processes. Okay? So at first glance, you would say, well, if it takes that long for half of a sample to decay, then it should take the same amount of time for the rest of the sample to decay, right? That is logically, it makes sense based on our everyday experience. But that is not at all what occurs, not even close. So to understand a half-life, well, first of all, we're going to talk about what kinds of decay we might be using. We're going to talk about some of the kinds of decay that can occur, and then we'll give a more specific example, and then we'll model it. The first kind of decay is called alpha decay. Alpha is the first letter of the Greek alphabet. That's where we get the word alphabet, from the first two letters of the Greek alphabet. And alpha decay looks a little tiny bit like nuclear fission, because what we are getting afterwards is a smaller nucleus, and fission splits a large unstable nucleus. But alpha decay does it in a very particular way, so it is distinguished from nuclear fission. It is not considered the same thing, even though you are winding up with a slightly smaller nucleus. So what happens? Well, it turns out that not just anything can break off of a nucleus. You might imagine that, well, if a nucleus is unstable, it could sort of shed whatever it needs to. It could sort of get rid of a neutron, or get rid of a proton, or get rid of, 5 protons and 3 neutrons if that makes it more stable. But it turns out that just doesn't happen. One of the only things that a nucleus can successfully shed, just sort of kick out, is what we call an alpha particle. It was called that because they observed it coming out of the nucleus before they realized what it actually was. When they examined it more closely, as you can see in this little cartoon, it was found to be a helium nucleus, just a regular helium-4 nucleus. Okay, so we call an alpha particle, we call a helium nucleus an alpha particle when it is ejected from a larger unstable nucleus. Okay, so a bunch of different elements will undergo alpha decay, and when they undergo alpha decay, well, then they've lost 2 protons. So then they always go down by 2 on the periodic table. Okay, so a lot of elements that alpha decay will drop back 2 elements on the periodic table to become whatever the element is that is 2 fewer than it is. For example, radon, number 86 on the periodic table, will alpha decay. It'll lose a helium nucleus. It'll just fly out of the nucleus. And then you'll be left with polonium, which is number 84. Polonium will also alpha decay, and it will release a helium nucleus. And that will produce number 82, which is lead. This is one of the ways that lead can be produced. So when I said that all the elements are formed by nuclear fusion, well, not always, because you can also form them from the decay of a larger nucleus. But the point is that alpha decay occurs without any provocation. Nothing triggers this. It just happens on its own. If you just wait and wait and wait, well, then eventually an unstable nucleus will throw out an alpha particle. So how long is that going to take? Well, that depends on how stable the nucleus is. The more stable it is, the longer it's going to take to throw out that alpha particle. But if it's very unstable, it could happen in just fractions of a second. Sometimes it happens like almost seemingly immediately. So alpha decay varies depending on the stability of the nucleus. Here's a little animation of alpha decay. So here we have a large unstable nucleus, let's say maybe polonium, and then it throws off a chunk. Now remember, the electrons are there. This happens even on Earth when you're not plasma. I'm just not showing them just to make the diagram simpler. They'd be a little bit further out anyway, but they would be protecting it. So nothing's going to get at this nucleus. It's pretty safe, okay, unless you were to exactly aim a neutron right at it, and that is unlikely to occur naturally. But just leaving it on its own, it's already unstable, so it does this to itself. It breaks off a chunk, which is an alpha particle, and then what we have left is now a different element. We've gone down by 2, so if that was polonium before, now it would be lead. It drops by 2 in atomic number and 4 in atomic mass. We'll discuss that a little bit later. Here we see a little image of some alpha particles being thrown out. So this is what we call a cloud chamber, where they evaporate alcohol vapor. I think this is one of the neatest things that I've ever seen. If you go to a museum that has a cloud chamber, you actually see the traces of these subatomic particles that are flying out of nuclei from radioactive decay. Okay, so what happens here, it's almost like a contrail when a plane flies over and you get condensation behind it. You're seeing the condensation of the alcohol into liquid, and that happens because of the ionizing radiation. You need enough radiation to do that. So the radiation can be in the form of an actual particle, like an alpha particle, or it can be in the form of electromagnetic radiation that can do this as well. So that's pretty cool, right? All of those are the traces. You're not seeing the alpha particle itself, of course, because that's way too small to see, but its energy is causing the condensation of the alcohol, okay? Really, really cool, I think. So what is going on here is this is radon gas. Radon gas is a radioactive gas, which you probably don't want to have around, okay? You probably don't want to have it around. The good thing about it is that it's relatively dense, so it's much denser than almost any other gas, so it's going to settle down lower. It often winds up in low places. Like, for example, in the basement. We don't have a lot of basements in California, but where I grew up in New Jersey, a lot of people have a basement and they have to worry about radon gas accumulating in their basement. This is a real problem that people have, especially in New Jersey. Okay, so alpha particles, they turn out they don't make it very far. They don't have a lot of what we call penetrating power, because pretty much anything will stop them, like a piece of paper, your skin will stop them. Pretty much anything they run into, they're not going to penetrate too far inside of things, so they're usually not considered to be the most hazardous form of radiation. Well, you don't want to get them inside your body, but as long as they're on the outside of your body, if you haven't eaten it or consumed it, well, then it's one of the more safe forms of radiation, okay? Not that any form is desirable. So alpha decay can be detected on a Geiger counter. If you get a Geiger counter out, it will detect a click for every one of these alpha particles that whizzes by it, okay? So alpha decay was the first kind of radioactive decay that was discovered. It's a helium nucleus basically breaking off of a larger unstable nucleus. And I guess this is another way that you can form helium, isn't it? So you can form helium, some of the helium that we have. In fact, most of the helium we have on Earth comes from this kind of decay. Interesting, right? So you can form helium from nuclear fusion, but you can also form it via alpha decay. It's one of the byproducts. And then pretty quickly it'll pick up some electrons and become a regular atom of helium. Pretty neat, right? Alpha decay. And here we see a little rock of radioactive uranium isotope producing a whole bunch of alpha particles in the surrounding vapor. You can sort of see where they're coming from in this one. By the way, I have my own Geiger counter. I actually have two of them. I'm going to be turning them on right now. And when I turn them on, you'll begin to hear, there we go, one of them. This one's got a little better. Here we go. You will hear these little clicks. By the way, those clicks, hear that? That is the detection of radiation around me. Now, you might be alarmed that there's radiation going on around me. It's also going around you, by the way. There's a normal background radiation rate. So hear those clicks? You can't predict when they're going to happen. There goes one. Notice how sometimes there's several in a row, and then there's a long pause between them. They're happening kind of randomly. So radiation is always going on around us, but as long as it's within an acceptable limit, it's considered normal, it's considered safe. If you're near, let's say, a nuclear power plant where there's been, like Chernobyl, or anywhere else that there's been any sort of problem, or if there's a natural occurrence of radioactive material, then you'll be exposed to a higher rate, okay? But these are the counts per minute. According to my little guide here, it says as long as you're within under 50 counts per minute, that means 50 of these in each minute, you are in the safe range. And it needs to be on a little time before you're sure what the count is. So I'm going to leave this running, and we'll see what the count is for me. Let's see if the two of them agree. Right now they're agreeing. Okay, let's see. Okay, so alpha decay, it's kind of cool to see where it's coming from. And here is another still photo of those alpha particles that are irradiating from the center, which is a radioactive sample. I believe this one is also an isotope of uranium, possibly uranium-235. So by the way, after uranium alpha decays, well, then it loses 2 protons as well as 2 neutrons, but the 2 protons change it. Uranium is number 92 if you look on your periodic table, and you wind up with only 90 protons, which is now thorium, okay? So interesting that you change the element naturally, And thorium is more stable than uranium, but thorium can also alpha decay down and it loses 2 more protons and it winds up being radium. Radium was actually named after the fact that it is radioactive. So interesting, right? There's a whole sequence that can occur, but each time you lose that alpha particle, then the nucleus is at least more stable. So when we say to decay to a stable isotope, it's got to be more stable than the previous one, but often there can be a whole sequence of radioactive decays that occur. So notice that this Geiger counter is still clicking. Let's see what it's settling on. Right now it says about 15 counts per minute on this one. The other one is measuring 17 counts per minute. So they're pretty much in agreement, okay? And if I leave them on long enough, they would have a greater sample size. But they're detecting, it's crazy to think that there's this much radiation around us naturally, even if we're in a normal place on Earth with no unusual radioactive activity. To understand the next kind of nuclear decay, you're going to need to look at things a certain way. I like to call this kind of voodoo chemistry. It seems kind of weird, but follow me here. Now, if you look at the masses of the electron, the proton, and the neutron, notice that the electron, as I said before, is a super lightweight. Okay, the mass of the electron doesn't even come close to the mass of one proton or one neutron. In fact, if the mass of the electron is 1, then the mass of a proton is 1,837. That is nearly 2,000 times greater than the mass of the electron. So even though electrons do have some mass, it is very tiny, like a little blip of mass. On the other hand, the neutron is pretty similar to the proton, 1,842. Very close. So there is a certain way of thinking about a neutron, of thinking about a proton with an electron sort of bottled up inside it. Now this might seem weird to you because how would that even work? It doesn't seem to work on a quantum level, but if you add together the proton and the electron, it's 1 plus and 1 minus. That equals 0, right? And the masses, well, they don't work out exactly, but there's a reason for that. They get pretty close. It gets closer, right? So for now, for this one, you have to sort of think of a neutron as a proton with a bottled up electron inside it. So just play along with me here. So if you take a proton and an electron, sort of squish them together, what you get is a neutron, at least in the case of what we're discussing here. This doesn't work in all situations. This isn't entirely true, really, but when they talk about a neutron star, guess what? That's what they mean. In a neutron star, the gravity has actually squeezed the electrons and protons together into neutrons. That's why it's called a neutron star. So in a certain point of view, this works. Here we go. So if a neutron is a bottled up electron inside a proton, what happens if the electron gets out? Well, then what are you left with? Well, just the proton, right? Because if it was a bottled up electron in a proton and then the electron escapes, well, now all that's left is the proton. Weird, right? Weird. Well, that is exactly what happens in our second kind of radioactive decay. No matter how strange that seems, that does occur. This is what we call beta decay. We call it beta decay because it's the second letter of the Greek alphabet. Alpha, beta, that's where we get alphabet, right? And some people, like the British, call it beta. I don't know which one is better, but they call it beta. And this occurs very commonly with a very abundant radioactive isotope, which is called carbon-14. Carbon-14 will beta decay, and it'll produce nitrogen, which is a different element. So that is a nuclear reaction, a nuclear process. But and they call the thing that flies out of the nucleus, this time it's not an alpha particle, it's a beta particle, okay, a beta particle. But when they looked a little more closely at what a beta particle really was, oh man, that thing is an electron, okay? Notice that there is also an antineutrino involved in this diagram, but the antineutrino is even smaller. Let's say An electron is so much smaller than a proton, right? Well, an antineutrino is like that much smaller than the electron. So it's a very, very minor element that I'm going to sort of gloss over here, okay? But they found it crazy that, wait a second, was that an electron flying out of a nucleus where there are no electrons? It seems bizarre, unless you think about that sort of voodoo chemistry of a neutron being a bottled up proton and electron. So look on the left where it says carbon-14, it says 6 protons and 8 neutrons, right? Look at that neutron on the very bottom, that sort of orange one on the bottom, right? Then after the beta decay, look at it again on the bottom. Now it's a proton. That's what's left behind when the beta particle escapes. And because you have an additional proton, well, obviously that changes the element. Remember, it's counting the protons that determines the element. So now it would have 7 protons, which of course would make it nitrogen. It still has the same number of objects in the nucleus, particles in the nucleus, so it's still 14, it's nitrogen 14. But now one of them, instead of being a neutron, is now a proton. Isn't that just crazy? So when they first discovered this, they didn't know what was going on, and it took a while to figure out why this was occurring. So here we have a carbon-14 nucleus, okay? It's about to beta decay. So watch that neutron. The neutrons in this case are green on the top, and watch what happens when that electron flies out. Now it is a proton, which makes the nucleus a nitrogen nucleus, the nucleus of a nitrogen atom. That is beta decay. Now notice this can happen even if it's protected by electrons. There can be electrons around there because it is doing it to itself. Nothing is making this happen, just waiting out the clock. Time. If you wait long enough, this will eventually occur to carbon-14. So here we see another one of those cloud chambers that detects radioactive decay, and what you're seeing mostly in this one are beta decay trails. So remember, these are ionizing radiation, so they're particles that shoot through and cause condensation of the alcohol in the path where they fall through. The alcohol becomes little liquid drops. And you notice that they're kind of squiggly. They're not straight lines anymore because these beta particles are very, very low mass. They're nowhere even close to the mass of an alpha particle, which would be something like, I don't know, 7,000 times more massive. And they are much more easily deviated by electromagnetic fields that are surrounding the area. But you can see all these little squiggly paths. I think it's really cool that both kinds of these new radioactive decay particles, the alpha particle and the beta particle, both show up again in these really, really cool cloud chambers. One of the neatest things you can see to delve into the microscopic world. So beta particles are a little bit harder to stop than alpha particles. Alpha particles you can stop with a sheet of paper, or just your clothing will stop them from penetrating inside your body. But beta particles, because they're much, much tinier and moving at a much higher velocity, they can actually penetrate a little bit further, but they can be stopped with something like an aluminum pan. Okay, so like a baking pan of aluminum, even if it's a little thinner than that. Aluminum foil might not stop them, but many layers of it would. So they're not that hard to stop. They're not the most damaging kinds of radiation. That would be gamma rays. Gamma rays are notoriously difficult to stop. Ask the Hulk. To stop gamma rays, you need blocks of lead or layers of concrete to protect you. That's why they put those around nuclear power plants. They usually have layers and layers of concrete. It's the cheapest way to stop gamma radiation from getting out. Anyway, those are beta particles, beta decay. And here's some still photos of the squiggly paths they follow. Nothing like the straight lines of the alpha particles. And this is partially because they are deflected by electromagnetic fields, like local electromagnetic fields. Because they're very, very low mass, it's much, much easier to deflect them with an electromagnetic field. Now, the very opposite of that can actually occur. This is a little bit different. This is not something we generally measure in the same way like with a half-life, but it is possible for an electron to actually hit the nucleus. Now, if you've ever thought about this, why doesn't the electron just hit the nucleus all the time if they're attracting each other? It's because the electron is moving too fast. The electron has too much energy to actually collide with the nucleus, but sometimes it's possible for the electron to lose just enough energy that it can actually strike the nucleus. Well, guess what? Whenever that happens, you wind up getting a nuclear process, a nuclear reaction. And this is called electron capture. So this is exactly the reverse of beta decay. Imagine an electron coming in and striking the nucleus. And when that happens, well, then it will sort of get bottled up inside a proton, turn the proton into essentially a neutron. So watch what happens. Here comes an electron. It hits that proton, and then it turns it kind of into a neutron. So it's going from nitrogen 14 back to carbon 14, the exact opposite of beta decay. Interesting, right? Interesting. One more thing I wanted to mention when we talked about why neutrons are unstable outside of the nucleus. Well, we didn't talk about why, but we talked about that they last about 15 minutes, right? So what do you think happens to that neutron after the 15 minutes? What do you think happens to it? It beta decays. So if a neutron is flying through space, after about 15 minutes, it will beta decay into a proton and an electron. Well, that's everything you need for hydrogen, isn't it? So it turns out that loose neutrons in the universe that are not found in a nucleus will beta decay after about 15 minutes, and you'll get a little bit more hydrogen because you've got a proton and an electron. That's exactly what you need for a hydrogen atom. So no wonder there's so much hydrogen everywhere. Okay. One more I wanted to talk about is positron emission. Now, positron emission, this is where it begins to boggle your mind, because we were talking about, okay, so if we think about a neutron as a proton with an electron bottled up inside it, then we can understand beta decay. The electron gets out and you're left with just the proton. And you can understand electron capture because an electron comes in, gets bottled up inside the proton, turning it into a neutron, right? Now, positron emissions, on the other hand, this has to do with antimatter. So what is a positron? A positron is just like an electron, but it's made of antimatter. And it has the opposite charge. It has a positive charge. So it turns out that losing a positron is exactly the same thing as gaining an electron. Okay? They call this the beta positive emission. This is another kind of beta decay, beta positive decay, because it's a positively charged particle. So again, losing a positron is like gaining an electron. So what do you think is going to happen? Positron emission follows the exact same pattern as electron capture. Okay? So watch what happens. Positron is emitted, but now a proton reverts to a neutron. Interesting, right? It's almost like gaining an electron. It's weird. I know it's complicated. And you might say, well, this is antimatter. We can't have that much antimatter in our universe, obviously. Everything around us is made of matter. So positron emission probably isn't such a big deal. Well, actually, positron emission can be very useful. They use it for a particular type of body scan called a PET scan. If you've ever heard of a PET scan, it isn't just used by veterinarians, it's also used by people doctors, okay, medical doctors. This is positron emission tomography. It is a way of mapping what is inside the body, especially soft tissue, using the emission of positrons. So if you can get positrons to be emitted, which we can, you can use them in interesting ways. So isn't it funny that we use antimatter in the medical field? Antimatter is a real thing, okay? And sometimes we sort of discount it. Here's an example of a sort of a positron emission scan. They have to adjust, and it doesn't really produce those colors. That's just a way of registering how much positron emission you're getting. And you can find problems, like obviously, I guess that's a problem inside this person's body. You can see what's going on underneath, kind of like we do with X-rays and MRIs, magnetic resonance imagery. This is another tool that they use in the medical profession, positron emission tomography. So now we get into the most useful thing about radioactive decay, radiocarbon dating. Now it doesn't only have to be with carbon, but this is a great example. This is one of the most commonly used ones, okay? Again, you can notice all those clicks still going on my Geiger counter here, okay? And it's still, now it says 20 counts per minute, okay? It will oscillate naturally a little bit up and down. So radiocarbon dating is a method for determining the age of something that contains carbon by comparing the amount of carbon-14, which is a radioactive form of carbon, to the amount of carbon-12 in the sample. So when an organism dies, because all living organisms contain carbon, they're always going to have a certain amount of carbon-14. The amount of carbon-14 it has will gradually decrease after it dies. So we can tell how long ago an organism died by comparing the carbon-14 to the regular carbon-12. Most of carbon is carbon-12. Over 99% of it is carbon-12. That's the most common and most stable form of carbon. That is not radioactive, okay? But the carbon-14 will always be present in a certain amount, a certain percentage, let's say like 1%. And then when the organism dies, that fraction will decrease. Instead of being 1%, it'll be like 0.5%, then it'll be 0.25%, it'll be dropping. And by using that measurement, we can tell how old the specimen is, like this stump here. When did this tree die? Well, they could radiocarbon date that. They could take out a sample of that stump, and they do this with anything that contains carbon. So carbon-14 is very useful for dating materials that come from a certain period of time. If we want to say like, oh, we find a fire pit, and in a fire pit, of course, you burn wood, and there's samples of carbon in the fire pit. It's a Native American fire pit, and you want to see, was it 5,000 years ago? Was it 10,000 years ago? Okay, that would be a great thing to use carbon-14 dating on. Okay, so remember, carbon-14 beta decays, and what it becomes is nitrogen-14. That is called the daughter isotope. The parent isotope is carbon-14. The daughter isotope is nitrogen-14, which is more stable. In fact, nitrogen-14 is extremely stable. How long does it take for that to happen? Well, the half-life of the parent is 5,730 years. So in 5,730 years, half of your sample will decay into nitrogen-14. But they don't compare the carbon to the nitrogen because every body also has nitrogen in it as well. Every tree, everything has nitrogen too. So you won't be able to compare those very well. But you can compare the carbon-14 to the regular old carbon-12 and find out how much should have been there to begin with, and how much is there now, and how much time has passed. The only problem with a half-life that's like 5,000 years is that you're only going to be able to date things going back a certain amount of time, maybe up to about 50,000 years. So we don't actually use carbon-14 for dating things like dinosaurs, things that occur millions of years ago, or even billions of years ago. We have to use something different, okay? We have to use different isotopes. Like, I don't know, what about this one, uranium-238? Now, uranium-238 isn't completely stable, but it's pretty close. It is technically radioactive, but its half-life is 4.5 billion years. 4.5 billion years. That is about the age of the planet Earth. So you can date really, really old samples using uranium-238, which will decay eventually into lead-206 through a series of decays, a series of alpha decays. And we can find uranium in many of our rocks. There's enough uranium that it's useful, okay? So if you want to date something like that was occurring hundreds of millions of years ago, you better not use carbon-14. You better use something like uranium-238, okay? On the other hand, there is potassium-40, which has a range sort of in between, a 1.3 billion year range. That means that the potassium-40 nucleus is fairly stable, just it's a little bit unstable. So if you wait long enough, some of them are going to decay. So what do they decay into? This is the interesting thing. Potassium-40 beta decays into argon-40. Okay. Now argon is actually something that you're breathing right now. It makes up 1% of the atmosphere. So where does all this argon come from? Well, guess what? The argon that you're breathing right now came from radioactive potassium in the earth. There's a lot of potassium in rocks, and the radioactive ones eventually decay and produce a little bit of argon. The argon turns out to stay in our atmosphere for a very long time, okay, because it's about the same density as regular air. And that's why you're breathing about 1% argon right now. Almost all of it was produced by the radioactive decay of potassium-40 in rocks. But don't worry, argon-40 is not radioactive and it's not at all dangerous. It's one of the most harmless elements there is, one of the most harmless atoms you could possibly encounter. It's hard to get it to do pretty much anything, which is why the name argon actually means lazy. So now let's try to understand how a half-life works. Here we have all these atoms here are carbon-14. Let's say we could somehow isolate the carbon-14 from the regular carbon, put that all together, and just sort of watch it on a microscopic level. Watch them decay. Well, after a certain amount of time, of course, if we just wait out the clock, we don't have to do anything to it. Some of those will decay. Now those would be nitrogen. Let's not worry about if they would disappear from our sample. Let's just keep them in place and show that those have now decayed into nitrogen. And then we just keep waiting and eventually more of them will decay. Well, you know what? I had no idea which ones were going to decay. They're sort of decaying at random, okay? But if I keep waiting, more will decay. And if I keep waiting, more will decay. And eventually we will reach a point where half of them have decayed. When we reach the point where half of them have decayed, that amount of time that we've waited is called the half-life. So again, this is a statistical thing. We don't know whether any specific atom is going to decay, but we know what the odds are. In that amount of time, 50% of them will have decayed. Half will have decayed, half will not. Okay, and then of course they don't just suddenly stop decaying after the half-life, they just keep on going. So what a lot of our intuition tells us is that if it took that long for half of them to decay, then it should take the same amount of time for the rest of them to decay. Because if it takes that long for 50%, it should take the same amount of time for the next 50%. But this is not at all what happens. They do keep decaying, but not the way you would expect. So let me show you what I mean. Here is a little bar. Let's say this bar represents carbon-14, okay? If we wait a certain amount of time, it will be decaying, okay? So we're waiting, waiting, waiting until half of it has decayed. That amount of time will be the half-life. Let's say that took 5,730 years, like it does for carbon-14. So now we've decayed half, and there is half left. So remember the definition of a half-life that I gave there? It was the amount of time necessary for half of your sample to decay. Well then, who says I had to start way back then? Why couldn't I start right now? And if I start right now, don't you think that all my sample of carbon-14 is just the 50% that is left? That is my whole sample now. So doesn't the definition of a half-life state that in a half-life, half of my sample will decay? So really, half of what is left will decay in the next half-life. Now this seems strange, because it seems like now it's going slower than it did initially. After the second half-life, 25% of your original sample remains. Well, that's weird. What's going to happen in the next half-life? Well, who's to say I couldn't start right now, and that what remains, that little quarter that's left, that 25% that is left, what if that were my whole sample? Well, in one half-life, half of my sample will decay. So we're going to divide that by 2. So by the time we get to the third half-life, it really appears that it's slowing down, and we only have 12.5% of the original sample left. And by the same logic, if that were my sample, if I were starting right there, then after one half-life, again, it's another 5,730 years. Each one of these intervals takes the same amount of time, then I would have 6.25% left, half of what we had before. That's after the fourth life. So you can notice here that it's taking a long time to get rid of the whole sample. In fact, if your sample is big enough, theoretically, you could say it would take an infinite amount of time. In practicality, your samples are never infinite. So really, you are going to get down to the point where you have either none left or a vanishingly small amount that's difficult to measure that is left. But you can have a fifth half-life, and notice we're getting down to a very, very small amount here. 3.125% left after the fifth half-life. And as you can see, we will keep dividing the amount by 2. And you can see this process occurring if you put in your calculator a very large number, like fill it up with 9s. Put in as many 9s as you can, right? And then divide by 2, right? Hit equals. Every time you hit equals, it'll continue to divide by 2. Keep hitting equals. See how many times you have to hit the equal sign to get down to a number that is less than 1. Because obviously you can't have less than 1 atom. You either have 1 atom, you can't have like half an atom. So that is sort of an example of how half-lives work. It seems weird, like why is it slowing down? Well, it's not really slowing down. What's happening here is the odds are 50-50 with every half-life. And they remain 50-50 for the next half-life. And they remain 50-50 for the next half-life. So it's more of a statistical rate than the kind of rate that we're used to. And we can model this very well by using pennies. Here we see the radioactive decay curve. Notice how we start measuring from half-life 0. Now it seems strange to plot 0 on a graph and not put it in the corner where the axes meet. Okay, but we like to plot the 0th half-life. It sounds weird, but it's important to put that. So whenever you're graphing half-lives, instead of starting out with half-life number 1, where you would normally put the 1, you put a 0, and you shift all the other numbers over by 1 to the right. Okay, this is the way we normally do it. And the 0th half-life would be like wherever you're starting. So if you're starting at a given point in time, that is the 0th half-life right there, boom, where you're starting. And you will have 100% or 1 whole amount of your sample. Then after 1 half-life, notice that it drops down to 1/2, half of your original sample, or 50%. And then at the next half-life, you will divide that by 2 again. You will have 1/4, 1/4, or that would be 25%, and so on, just like we just saw on the bar graph before, on the bar diagram before. So notice how this radioactive decay curve works for any radioactive element. Not just carbon-14, this exact same curve would work for any radioactive material. Interesting, right? The only thing that would change would be the interval between the half-lives, the length of the half-life itself. So some things have half-lives that are very short, fractions of a second. Some have half-lives that are hours. Some have years, thousands of years, millions, or billions of years. But the decay curve will still look the same because it's still a statistical rate, 50-50, every half-life, 50% of your sample will decay. This works way better when you have larger samples. It gets a little iffy if your sample is very, very tiny, but generally, even if you have just a scoop of something, that would be enough because you would have quadrillions of atoms, and that's enough to get it to match this radioactive decay curve very, very well. But we're going to be modeling it with pennies. We're only going to be using 100 of them, and so it doesn't match it quite as perfectly, but it's still surprisingly close. So here is the analogy. This analogy really helps you understand how half-lives work. We're starting out with pennies. All of these pennies are carbon-14. They're all tails. Tails represents carbon-14. That means they have not yet decayed. But as you know, if I flip coins, well, they're not all going to come up tails again. That's not going to happen. And let's ignore the ones that land on their side, like in the twilight zone, where a coin lands on its side. Let's just say they either have to land heads or tails, right? And the ones that land as heads, after you flip them all, those have decayed. So as you can expect, flipping heads and tails, it's pretty close to 50-50, right? The odds of getting heads and tails are going to be 50-50. So then about half of them will decay. Well, that's just like a half-life, isn't it? That's like the first half-life. But now those ones that have decayed, they are no longer carbon-14, so they are no longer part of your new sample, no part of your remaining sample. So let's take those heads out. When you take the heads out, notice that you've got about half the coins left. But the odds when you flip them is still going to be 50-50, isn't it? That you get heads and tails. Do you see what's happening here? We're seeing a statistical process, sort of a statistical rate, a 50-50% odds that you're going to get heads and tails each time you flip. So each time you flip the coins, it would be like having another half-life, going the amount of time, like for carbon-14, 5,730 years. So after one half-life, the likelihood of each nucleus having decayed is 50%. So again, the heads are the decayed nuclei. They have become nitrogen. They're no longer carbon-14, which is why we remove them from the sample, and then we continue only with the ones that are still carbon-14 to see if they will decay in the next sample, but of course they will not all decay because the odds are 50-50. And then we continue and continue and continue until all of the carbon-14 have decayed into nitrogen. Now we can do this with 100 coins because it's a very limited sample. It would take a lot longer to get them all to turn into carbon-14. Let's say if we had 1,000,000 pennies or 1,000,000,000 pennies, right? So that's a great way of understanding the way half-lives work. Notice that it's very counterintuitive, but we can still understand it with a very simple model like flipping coins. So that is the end of the notes on half-life. Okay, now we have a better understanding of the natural nuclear processes that are occurring all around us.